thanks so much for having me. And this is the second time I've given a talk in Boulder, and just sort of been forget that people come from across town, and sort of like people walk in, and I'm like, oh, thanks for coming. I didn't know you'd be here. So that's really, really nice, and it's nice to see people I know. Yeah. So today I'm going to focus on atmospheric organics and the role they play, or the role they may play, and the uncertainties in the role they play in terms of creating cloud condensation nuclei, which are the particles on which cloud droplets form, and the effects that these can have on climate. So I'm going to start with a quick review of sort of the basics of aerosol microphysics and the way which particles create these cloud condensation nuclei in the atmosphere. And then I'm going to sort of have two parts to my talk. The first is going to be sort of general uncertainties in the secondary organic aerosol amount and the way in which organic species condense onto particles and the way in which they affect CCN and climate. And the second part of the talk is going to be focusing on a short-lived reactive gas phase species, a group of species called Criegee intermediates. And about a year ago, a bunch of Nature papers, or two science papers, excuse me, came out and discussed how these Criegee intermediates can react with SO2 in the atmosphere. And there's a bunch of hype, for lack of a better term, on how the role which these reactions may play on CCN and climate. And so we actually did some exploring to see what these reactions might actually do in terms of affecting CCN and climate. So this is the world that I live in. I like to think of the aerosol size distribution and trying to get this correct in models. I've broken it up into two modes of the size distribution that contain most of the number of particles in the atmosphere. There's a coarse mode that's missing, but that doesn't contain a majority of the number in most parts of the atmosphere. And occasionally, if you have nucleation occurring, you'll also have a nucleation mode. But most of the time, most of the particles exist in what we call an ultrafine mode or an Aitken mode, or the accumulation mode. And I've sort of put as a rough division line between the two as about 100 nanometers. And so smaller particles are in this Aitken mode generally, and larger particles are in this accumulation mode. The accumulation mode is the one that we need to get right in our models, because these are the ones that have the climate effects. These are the particles that are large enough to act as cloud condensation nuclei. So when most clouds form, they're forming on particles that are larger than about 100 nanometers, or if you have a convective cloud, maybe 30 nanometers or larger. And these are also the particles that dominate scattering and absorption in most parts of the atmosphere. However, even though these particles are generally too small to directly affect climate, they can grow through condensation to become accumulation mode particles, or they can be lost through coagulation before reaching accumulation mode sizes. So there's a competition between these two that we'll talk about today. And most particles in the atmosphere, by number, are formed by nucleation into this Aitken mode, although primary emissions also move particles into the Aitken mode, and many particles in the accumulation mode are brought there straight through primary emissions. And we also need to get deposition right. So in terms of modeling these things, which is what I try to do, there's a lot of things we need to get right if we want to get the size distribution right. And I don't have time today, unfortunately, to talk about what we know and don't know about all these things, but there are certainly a lot of things about each of these processes that we don't know. What I'm going to focus on today, for the most part, is ultrafine particles, the creation of them through nucleation and primary emissions, and then how do these particles actually reach sizes where they can affect climate. And so if a particle forms through nucleation, so if you have vapors that are low volatility and really want to be condensed to something, but if they can't find aerosol surface area quick enough, they're going to form new particles that are size about 1 nanometer. And similarly, a lot of combustion emissions make particles in the ultrafine sizes. They can grow through condensation to become CCN if they don't coagulate with a pre-existing particle first. So this competition between coagulation and condensation is the inspiration of this cartoon that my friend Ilona Rippinen and Hanna-Pekka Maki put together for their paper. And so we have particles that are formed, say, through nucleation that are sizes, diameters of about 1 nanometer. In order to affect climate, they need to make it to sizes of about 100 nanometers. So these small particles are growing, or running, in this case, through condensation, and trying to make it to larger sizes. But these pre-existing bigger particles are on the opposing team, and if they happen to bump into one of these small particles that are trying to reach climatic relevance, they're just going to sort of grab them and absorb them as part of them. And these particles will not contribute new particle number, new CCN to the climate. And they sort of, in Finland, they're both Finnish, and in Finland they really like nucleation. And so, the whole connection between nucleation and climate. So they have the condensing team, the nucleated particles making it to climatic relevance, actually winning against the coagulation team. But this isn't always the case in the atmosphere. So again, this is the picture we're going to primarily focus on today. Oh, I must have gone back one. But so the whole talk is going to focus on organics, and so I've taken this cartoon from Jose Jimenez's 2009 paper, where they synthesize what we sort of know about organic aerosol in the atmosphere, largely through the aerosol mass spectrometer. And so this is showing aerosol mass concentrations measured by the AMS at many different locations. And these shades of greens through gray are all different types of organic aerosol that are classified through the AMS. And I just have put this up here to just sort of show that throughout at least the continental boundary layer where most of these measurements are, the organics take up some significant fraction. Some of the smallest ones are maybe 20% or so, but then many of the largest ones are more than 50% of the submicron mass of aerosols or organics. And so organics being many, many hundreds or thousands of different species in the atmosphere, it's a difficult thing for us to get right. And so it's of the species that we tend to think about in terms of, for submicron aerosol, sulfate, nitrate, ammonium, it's the one which we sort of have currently the lowest handle on. And so, but if we actually want to get the competition of these small particles growing to CCN sizes right, we need to get the organics right. And so there's a few questions that have sort of been things that my group has been looking at over the past several years in dealing with secondary organic aerosol in models. And so the first question is, when we have secondary organic aerosol that's forming, so this is secondary organic aerosols when you have volatile organic compounds in the atmosphere and they oxidize in the atmosphere, that you create products that are lower volatility and want to stick to the aerosol phase. But a major question for people who look at aerosol microphysics is are these organics, these secondary organics, partitioning into the mass of the particles that are already of CCN sizes primarily, or are a significant fraction of them condensing to the ultrafine particles that are too small and growing these particles to larger sizes? So we'll touch on this, and then we want to look at how sensitive the model cloud condensation nuclei predictions are to and size distributions are to the total amount of SOA, since this is uncertain in the models, and trying to figure out through using measurements if we can sort of optimize our model inputs on these in order to make an optimized model. And so I'll touch on these. And this is being led by my graduate student, Steve DeAndrea, with inputs from quite a few other people that I have up here. So to motivate this and sort of discuss how important we know secondary organic aerosol can be to the growth of small particles in the atmosphere, what this is showing here is measurements from 1 year at a station in Finland called Huittila. And this is the measured growth rate of particles that have recently nucleated. So these are particles that nucleated and then are growing through condensation of sulfuric acid in organics. And through measurements of the way the size changes with time, they're able to calculate, on average, as a function of month of the year, how quick are the 1.5 to 3 nanometer particles growing, the 3 to 7 nanometers particles, and the 7 to 20 nanometer particles. And these growth rates, what I want you to take away from this is these growth rates are on the order of several nanometers per hour. So this is ranging between about 2 and 8. And there's some dependence on the size, but we won't worry about that right now. But what I want to show here is this is the maximum growth rate that the condensation of sulfuric acid alone can account for. And so that they measured sulfuric acid concentrations and then calculated how much of the growth can come from sulfuric acid. And I want to note that the scale here is different. So this scale only goes from 0 to 0.5 nanometers per hour. And so what we see is that sulfuric acid is not creating most of the growth, in this location in Finland, the organic condensation is. And so the reason why this is important is in the early microphysics models, we didn't necessarily have, many of the models didn't have SOA condensation onto these ultrafine particles growing them. So we were underestimating our growth by only assuming that the sulfuric acid, which we know was very low volatility, was the only species that was condensing onto these particles. So this really motivates us to make sure we get the condensation of SOA onto these small particles correct. Because if they grow too slowly, those big coagulators are going to get them before they get to the CCN sizes. But if they grow quickly, they're able to sort of run quickly past those coagulating particles and make it to CCN sizes. So then the major question for me was, how does volatility of the SOA affect the condensation onto these small particles? And so people who had researched SOA in sort of a general bulk mass sense found that a lot of the SOA was what was called semi-volatile, meaning that the SOA was sort of relatively equally happy being in the gas phase versus the particle phase. And these have, for people who actually think about volatility, these have saturation concentrations on the order of 1 microgram per meter cubed. But if SOA is very low volatility, meaning it really only wants to be stuck to the particles, we have what we call low volatility SOA. In which case, if you form secondary organic aerosol molecule through chemistry in the gas phase, the first surface it finds is going to stick to, and it's not going to want to re-evaporate during the time that the aerosol is in the atmosphere. And so essentially the amount of condensation to a particle depends on the particle's surface area, or Fuchs corrected surface area, which is, accounts for the physical differences between the smallest particles and sort of the larger particles. So, but the small particles, they're getting less of the mass of the SOA that's forming, but they're still getting a substantial amount of it compared to if the SOA is semi-volatile. Then what happens is you end up having SOA that forms, it sticks initially to the particle, but then it will re-evaporate again after some time, and it can recondense again. So it's sort of in equilibrium partitioning between the aerosol phase and the gas phase. And what ends up happening is your small particles will reach equilibrium very, very quickly because there's not a lot of mass to partition into, whereas the bigger particles will take longer to reach equilibrium. And when you're out of equilibrium, when you're forming SOA, this means you get a larger net condensation. And so here the net condensation was proportional to the surface area, but if you have the semi-volatile species, the net condensation is proportional to the mass. And since larger particles have a significant fraction of the mass and these small particles carry very little of the mass, if you have semi-volatile SOA, almost none of the SOA is going to go to these small particles. So the take home from this is that these, if we're looking at the nucleated particles growing to CCN sizes, if the SOA ends up being very low volatility, these small particles are going to do better, are going to grow much more quickly in this low volatility regime than they would if it was a semi-volatile regime. So we explored this using a bunch of field data. So we took different days, and this is the size of particles as a function of time, hour, and the day. And here we have a nucleation event. So this is particles, this is concentration of particles as shown by the color. So we have particle formation happening in the late morning, and then condensation onto these particles grows them up to about 20 or 30 nanometers. So this is measured data in the field. This is from Huhtila in Finland. So then what we did in our model is we constrained the model with the initial size distribution of the day. We constrained the total amount of mass condensed based on what was measured that day. And we specified the nucleation rate based on what was measured that day. The only thing we changed was how much of this of the material is sort of semi-volatile versus low volatility. And we assume it to be semi-volatile, almost all of the mass ends up partitioning into the more massive accumulation mode particles, whereas if it was low volatility, it ends up being able to more effectively condense to these smaller particles and grow them to the sizes that were observed on that day. And if we have some sort of mixture, you get something in between, but we actually weren't able to reproduce that growth entirely. So what the lesson from this was, at least on this day, is that there must be some fraction of the SOA that's forming that really is sticky and low volatility and wants to just condense the surface area, which isn't necessarily consistent with what is found in lab studies when they actually measure the volatility of the species that goes on. So there's some interesting chemistry going on here in the small particles that isn't totally understood, and this is one of the main things that Jim Smith's group And Jim Smith, who's here, is trying to understand the chemistry in these small growing particles. So to sort of summarize a number of different days, we looked at trying to figure out, sort of comparing what diameter does the measured day grow to on that day versus the model day. And we want to get the two to match. So if I took a whole bunch of different days and plot them, the model diameter at the end of the event versus the measured diameter at the end of the event, and each of these different colors represents a different assumption about the volatility. In order to get match on the 1-to-1 line here, we needed to assume very low volatility. So these are C stars of 10 to the minus 4, 10 to the minus 3 for people who think about these types of values. But the take home here is that, yeah, we couldn't get matches if we assumed that much of this material at all was semi-volatile. So essentially, we're making SOA, and the only way we can reproduce the growth is if it is very, very low volatility. So what does this actually mean in terms of global CCN and climate? So we tested this in our global model, which is the GeoSchem general chemical transport model, where we've incorporated the TOMOS microphysics. So we simulate the aerosol size distribution using 40 size sections from 1 nanometer to 10 microns. And we simulate microphysics such as condensation, coagulation, and nucleation. And we have a whole bunch of different aerosol species. So what these maps show is if we were to assume that our aerosol was semi-volatile, and the SOA condenses to the mass, versus if we assume the SOA is low volatility, what's the ratio in terms of different size particles? How many particles do we have? And so a red color percent change is more particles if it's semi-volatile. And this is N3 is the total number of particles larger than 3 nanometers. And so this is essentially all particles in the model. Number of particles larger than 10, number of particles larger than 40, and number of particles larger than 80. So these are more our climate relevant sizes here. And what this shows is that in regions where we expect there to be lots of secondary organic aerosol, which are regions where there's lots of VOCs coming from vegetation, we end up seeing enhancements in the CCN in these regions by as large as over 50 or over 100% in these regions by switching from assuming that it was semi-volatile where it doesn't go to the small particles to assuming that it's low volatility where it goes to the small particles and grows them to CCN sizes. There's essentially no change over most remote regions, which is a little surprising that there isn't much blowout from the continents of these particles, but over the continents we do see these large percent changes. And I should point out, sorry, this is just at the boundary layer that we're looking at here. And also, importantly, these simulations, we only consider biogenic secondary organic aerosol. So we only have 19 teragrams of SOA per year, which leads me to the next point, is that there's uncertainty in exactly how much SOA there is. And so how sensitive are our predictions of CCN to that? So going back to Jose's figure here, I didn't show a comparison, but we tend to, in many of these places, underpredict the total mass of SOA in most of these locations in the model when we only consider those vegetation biogenic sources of SOA. So in a paper that Jose did with Dom Spracklin, what they tried to do was get closure by using a similar model to what I just showed and trying to see how much extra SOA do they need to add in order to match these AMS measurements, as well as what locations do they actually need to emit the SOA from. So in their model, they have similar biogenic SOA to what we have using, we end up using the Megan inventory, which is what Alex Gunther developed. I can't remember what biogenic SOA Dom used, but something similar to that. So they have 13 teragrams per year, so similar to ours. They have a small amount of biomass burning SOA that's small enough that I'm not really going to talk about it today. As well as what they really need to get closure is this 100 teragrams per year of anthropogenically controlled or anthropogenically influenced SOA. So this is, when what they did for these emissions of this is they just scaled this 100 teragrams per year with the carbon monoxide, anthropogenic carbon monoxide emissions. And it's not clear whether or not this is actually anthropogenic SOA itself, or whether it's just anthropogenic pollution influencing biogenic SOA from forming. And there's some carbon dating stuff that data that Dom used to actually show that it seems like that this is actually just anthropogenic pollution influencing biogenic SOA. And that's a whole other field of study that I know a number of other people here are interested in too. But what we wanted to show here is how sensitive our CCN simulations to the addition of this extra SOA that we're missing. And what goes on here is actually quite a bit interesting because you get to see a whole bunch of blues and a whole bunch of reds in this. And so this is the ratio of when we had our original, or when we add in our extra SOA, dividing it by the original SOA. And so anything that's blue here means that there were more particles when we did not have the extra anthropogenic SOA. And if there are reds, there's more particles when we added in the extra SOA. So I'll start with the CCN here because it's actually a bit easier to explain. So over continents, our larger particles, the one's larger than 80 and one's larger than 40, we get big, big enhancements larger than 100% over many anthropogenic regions where there's lots of CO emissions, so therefore we have lots of anthropogenically influenced SOA. And so we get big enhancements over Asia, Europe, North America. What this ends up creating, though, is a feedback where we have a lot more big particles, and this reduces the amount of particles that nucleate because there's larger surface area particles. It increases the amount of coagulation of these small particles with the big particles, as well as it grows the small particles to bigger sizes more quickly. And so we end up having smaller numbers of our small particles, whereas we have larger numbers of our bigger particles. And there's even some feedback over the oceans where, because we have more large particles, the size of our CCN has grown. This actually reduces the number of CCN downwind through feedbacks. So we have a whole bunch of different simulations here where we've shown that things change by quite a bit, but how do we know which ones are right? So this is where Steve is working on right now, and he just actually made these figures for me in the past week, so we haven't fully digested them. And you're not going to obviously digest these at all because I just threw up 15, 18 panels all at once. So I'm going to show more of a summary of this on the next slide. But what we've done is we've taken measured size distributions, that's the black line, from a whole bunch of different SMPS, scanning mobility particle sizer data from around the world. And we're trying to see which simulations tend to match these best on average. So don't worry about the exact details of all of these. I just want to show you that this is what we're sort of working through right now. And so we have both surface area condensation with our biogenic only simulations, mask partitioning for semi-volatile species with our biogenic only, as well as the same two, but with our extra 100 teragrams per year. So the synthesis of all these data is shown here. And so this column is for our total number of particles larger than 10. This is total number of particles larger than 40, and total number of particles larger than 80. So we're getting to bigger sizes as we move to the right. Along this line is if we condense to the surface area, so this is low volatility with biogenic SOA only, partition to the mass with biogenic SOA only, condense the surface area with including also this extra 100 teragrams of anthropogenically influenced SOA, and same to the mass. Actually, no, I swapped these two. This should be the surface area, and this should be the mass. But what we're doing here is for all these sites, we're plotting the measured, modeled versus measured. And we're trying to see through metrics of bias, the slope, and R squared if we're sort of doing things better or doing things worse. And in general, there's actually not as much of a change as I was anticipating, because what we actually see here is that lots of the change actually happens in the smallest particles. And by the time we're sort of looking at this here is, sorry, I apologize, this is hard for you to see, 10 nanometers and 100 nanometers. By the time we get up to 100 nanometers, there's not as much of a change. So it's a bit tricky to sort of optimize this. And the other issue is that we're only changing things here in terms of the SOA. There's also uncertainties in primary emissions rates that are going to cause this comparison to change. Uncertainties in nucleation rates, uncertainties in deposition. And so, our hopes is to try to sort of optimize what's the best SOA assumptions we can make in order to get the size distribution right, but it's possible that we could get things right for the wrong reason if we also happen to be doing the wrong emissions diameter or the wrong nucleation theory or so on and so forth. That's the toughest thing about these models is we have 5 billion knobs, and you try to get the right answer, and it's just really difficult to do. So, but anyways, we try. And occasionally we find something interesting and useful, so that's what we hold on to. So many conclusions from the first part of the talk is that CCN predictions are strongly sensitive to assumptions about SOA, particularly over continental regions. And so there's uncertainties here with surface condensation versus this thermodynamic partitioning. So this is low volatility. If the SOA is low volatility versus if it's more semi-volatile. As well as there's some sensitivity to how much the Kelvin effect is going to affect partitioning to the smallest particles. And we've been doing this, but I haven't covered this here. As well as some big uncertainties in terms of the SOA amount. And what we're trying to do now is figure out if we can use these size distribution measurements to really constrain what's going on the global scale. So now I want to switch gears a little bit and talk about this Criegee intermediate plus SO2 chemistry and CCN. And so about a year ago, Dom Sprackland and I were talking at a meeting, and we were talking about these a pair of papers that came out in Science that were talking about Criegee plus SO2, and we're like, well, we have the tools to actually determine what this means for climate, and so this is what came out of that. And so organics are going to be part of this, and I'm going to continue to talk about that, but there's a big portion of this deals with SO2, so now I'm going to sort of take it back a step and talk about SO2 fates in the atmosphere. So we have SO2 emitted in the atmosphere both through biogenic sources, through DMS, and through, or volcanoes, and anthropogenic sources, say power plants. And so a large fraction of this is going to be lost through wet and dry deposition before it actually forms any aerosol in the atmosphere. And I've sort of taken these percentages out of Geochem. There's different models will say different percentages, but it's generally on the order of about 2/3 will be lost through deposition. About a quarter of it is going to react in the aqueous phase with hydrogen peroxide or ozone to form aerosol sulfate. And traditionally, the traditional view is about 15% or so will react in the gas phase with OH to form sulfuric acid. And this is the pathway that really matters for nucleation and growth. And so in order to have nucleation in the atmosphere, we know nucleation involves sulfuric acid. And so and also sulfuric acid is one of the main species contributing to the growth of these particles. And so getting this pathway correct, and this, I say approximately 15%, but if there's uncertainties in exactly how much goes through this pathway, this would lead to uncertainties in nucleation and growth. And so what these papers about the Criegee intermediate brought up is that what if there's another oxidant in the atmosphere that can react with SO2 in the gas phase to form sulfuric acid? And what if this percent that we were predicting for our gas phase oxidation pathway is incorrect? Could there potentially be, are we potentially predicting the wrong amount of sulfuric acid, and will this affect our predictions of CCN and climate in the atmosphere? And so, yes, if we get our sulfuric acid, say we're under-predicting it and we should have more, we should, in theory, have more nucleation and faster condensation. And so this should, in theory, be helping us make more CCN in the atmosphere. So I'm going to talk a little bit about the two science papers that came out at the beginning of the year. I'll actually start with the second one because it helps me motivate things a bit more. And so this came out of a group, by a group in Finland, and the first author is Malden. And what they ended up doing is they have measurements of sulfuric acid in the atmosphere, and that's plotted on this axis. And if they were to model based on OH concentrations and SO2 concentrations, what they would expect the sulfuric acid, the calculated sulfuric acid to be, they also need a condensation sink in order to make this calculation. But when they do this calculation, they were always about a factor of 2 or so low. They were not able to get closure between their calculated sulfuric acid and what they were actually measuring. And so what they needed to do is have some correction on this in order to get to the one-to-one line, and they're saying there's some sort of non-OH oxidant of sulfuric acid. And they did experiments where they, and this is the concentration of sulfuric acid through the black line is measured, and then the OH is what they would get through the calculation, and that's this red line, and then the blue line is the amount of sulfuric acid that was formed through some other oxidant. And in their experiments, they have, if they bring in ambient air, they're getting a certain concentration of sulfuric acid. If they expose it to emissions from different kinds of trees, they get increases in this. So this led them to believe that this extra oxidant for sulfuric acid is associated somehow with the emissions from trees. And so they have brought up the question, is this extra oxidant X what's called the Criegee intermediate? And the Criegee intermediate is formed when you have alkenes in the atmosphere that undergo ozonolysis. And so trees give off terpenes and isoprene that have these alkene groups and can form these Criegee intermediates. And so you have ozonolysis, and what you end up forming is a aldehyde or a ketone, as well as what's called this Criegee intermediate, which they call a biradical. It's more of a Spitter ion that has these very reactive two oxygens, one which tends to hog an electron, the other one that tends to be wanting an electron. And so these are very reactive. And it's been known that this Criegee intermediate reacts with SO2 to form SO3, the same steps here that when you have OH plus SO2, and then this can go on to react with water to form sulfuric acid. So the other science paper that came out was by Welts, and this is the first one that came out, and they were measuring the reaction rates between the Criegee intermediate and SO2 and found it to be a few orders of magnitude faster than what was previously had in like the NIST literature. And so I don't know why it was slower before, or what they were doing exactly differently to get it to be faster. But both the Malden paper and the Welts paper showed that the reaction rate between SO2 and the Criegee intermediate needs to be a good deal faster than what was thought before. And so what this means, in regions where we have alkenes, we're going to be forming the Criegee intermediate. We're going to be creating more sulfuric acid. We can have more nucleation and potentially more growth. So on that Welts paper were a bunch of chemists from Manchester, and I don't know the full story, but I know that they were not 100% behind the press release that was released by the University of Manchester about their own research. And so the University of Manchester, I think, went and interviewed the researchers. I really should get entirely the full story on this, and then released this press release that's titled, "Researchers Discover Particle Which Could Cool the Planet." And so I find this interesting on a few levels because the Criegee intermediates, if they have the potential to cool the planet, they're already doing it because the Criegee intermediates formed from alkenes that are already being formed from VOCs. I'll show a few more of these and then I'll talk about it more. So after this initial press release, a lot of if you search for Criegee intermediate, you'll get all of these news stories that come up, and it's really, really entertaining. So if you just click on, within like the first 2 pages of Google hits, you get things like, how mysterious molecules may help cool the planet, newly discovered molecule has the potential to offset climate change and cool the planet, offsetting global warming, molecule in the Earth's atmosphere could cool the planet, and the new molecule could be the key to stopping climate change. So then I started thinking through, how do we actually stop climate change through the Criegee intermediate? We'd have to add more alkenes to the atmosphere in order to make more Criegee intermediates. So, but aerosols only have a lifetime of about a week, so we'd be creating CCN, but all these alkenes are going to make CO2 eventually. So I don't know if we'd ever get a net benefit by trying to curb climate change to this molecule. So I'm not totally sure how they got to this. I could see that there was potentially this forcing that was cooling climate already that we're missing, but nothing about using this to actually, say, geoengineer or whatnot. But my favorite one came from, I guess it's the A register, or it's just the register. Pollution gobbling molecules in global warming smackdown, all caps. Newly observed particles scrub our filthy air. There's always this, people who sort of combine climate effects from pollution effects, and I don't know if necessarily going from taking SO2 more quickly to sulfuric acid really makes things cleaner. I mean, I guess we regulate both SO2 and aerosol, but still. But this one's the craziest, but then when I actually looked at some of the links off this webpage to other stories on the webpage, there was this one. heavily armed sex-crazed dolphins on rampage in Black Sea, naval cetaceans with guns on heads seeking females. So I didn't actually have enough time to really investigate that more, but I stopped there and I realized maybe this isn't the most reliable news source anyways. But so what happened here is that there was a whole bunch of media, maybe not CNN type media, but science type media on the web that really jumped on something where all they had was the first chemical steps, and no one had actually quantified a connection between these molecules and climate. And so what we wanted to do is actually draw that link of how much of an effect do these molecules actually have on climate. And that's why Dom and I were so interested on it, is we had seen a few of these and we really were saying, we don't have any idea what effect these have on climate. So this mechanism that I showed a moment ago, what we did is we added this to the chemistry in geochem and allowed it to affect our microphysics. So this is the same model I showed you before. And what we did is we added Criegee formation from isoprene, as well as isoprene products, methacrylene, methyl-vinyl ketone. We have Criegee intermediate formation from monoterpenes, as well as the anthropogenic propene. And what we did is we assumed the rate constants, the fastest rate constants from those two papers, to sort of give what we think is maybe an upper bound in terms of the rate constant between the Criegee intermediates and SO2. So just to sort of show the global picture in terms of SO2 loss pathways, before we put in the Criegee intermediate chemistry, this pi is what we had. And so when SO2 enters the atmosphere, this is roughly 60% of it's being lost through wet depth, 25% through aqueous chemistry, and about 13% through loss with OH. Globally, when we add in the Criegee only ends up taking this 0.4% slice. But it still could do things maybe regionally that are important. But that's just because we included the whole troposphere and the oceans where we don't have any actual alkene emissions. So thinking things more spatially, this is where Criegees are being produced. And it essentially is following where we end up having biogenic alkene emissions and maybe some anthropogenic propene emissions. So we're seeing it where in the forests where we end up having lots of emissions. We need to also superimpose this on the fraction of the Criegee intermediates that actually react with SO2. So Criegees react quite readily with water vapor. And actually, that's the dominant loss of Criegee intermediates globally. And so any region where we don't have a lot of SO2 and it's humid, almost all the Criegee intermediates are just going to react with water vapor. So we only end up, this is percent, from 5% to 55%. So only in regions where there's a ton of SO2 or very low water vapor, such as the poles, do we end up getting any significant fraction of the Criegee intermediates reacting with SO2 as opposed to water vapor. So this is how much we increase our sulfuric acid concentration due to the addition of this chemistry. So this is a percent change between our model cases without the chemistry versus adding in this Criegee plus SO2 chemistry. The left side is annual average, and then the right side is in July, just because it lights up the northern hemisphere a bit more, where a lot of the research has been done on this, such as in the Malden paper. Most of the largest percent changes happen in the tropics, where we have lots of isoprene emissions. And this is even true in the July simulation. What's weird here in the Arctic, what's going on in the Antarctic here in July is just that there's no sunlight, so there's essentially no OH. But if you can get Criegees through ozone transport into these regions, you get large fractional changes, but still the absolute changes here are tiny. It's just that we're dividing by something very close to zero. The main reason for these huge enhancements, over 400% increases in sulfuric acid in these regions, is that one, SO2 is generally quite low, and two, this is OH. Our OH concentrations in geochem are very, very low in these regions because in the high isoprene regions, our chemistry is predicting it to be quite low. This isn't necessarily correct, but it is one of the reasons why we're getting very high enhancements in these regions, is that there just isn't a lot of OH oxidation in these regions happening. And then as soon as we add an oxidant in, it's going to increase the sulfuric acid by quite a bit. So now stepping from sulfuric acid, how does this affect our particle concentrations? Here I'm plotting, this is the total number, change in the total number of particles larger than 10, total number of particles larger than 80. So total particles, CCN size particles. This is annual mean, this is July. And as you'd expect, the regions that had the big enhancements in sulfuric acid are going to have the bigger enhancements in total particle number. And so throughout the tropics, we're getting something now on the order of, mostly 25% and lower, with a few exceptions in the Amazon region. And then there's some sort of northern hemisphere enhancements too, but on small sort of 1 to 5% type scales. So the dampening here is we're getting large enhancements in sulfuric acid, as I showed before, but then the actual changes in particles are much smaller due to feedbacks. We end up having faster nucleation initially, but this creates more particles, increases the condensation and coagulation sinks, and so the whole system is that the total number of particles is dampened, and the CCN particles are dampened by even more. And you can see the largest enhancements in the Amazon are still only 5 to 15% for our CCN. And this is due to just the fact the interactions and the dampening within the system. So even though there's this whole chemistry that we were leaving out, we're still only changing our CCN at most by 15% in the regions where the chemistry is happening most vigorously. And then throughout most of the globe, we're not getting any changes at all. And just comparing to measurements in two different places, this is in the middle of the Amazon for the Amaze site, right in the heart of where the biggest changes are. And that's this plot here. If you look at the difference between the solid blue and the solid red lines, that's a difference in the size distribution that we get from having that chemistry turned on when you move from the blue line to the red line. The black line are the measurements. And then the dashed lines are the without Criegee and with Criegee when we add in the extra 100 teragrams of SOA. And so what we're seeing here is that the model's wrong, and that the changes we get from switching on this chemistry are much smaller than the amount that the model is wrong by. And so we're getting some correction here, but clearly there's other reasons why the model is incorrect, and that the Criegee intermediate influence is not the major reason why. And this is in the region where we get the biggest change. And so if we can't even get a major change there, it just shows that our models were not being limited by lack of this chemistry, they're being limited by other things. And then in the northern hemisphere in Hutula, there's almost very small differences between the blue and red lines. And that, again, there's things we need to improve in the model that are completely different from this chemistry. In this one, we took all the way to radiative forcing. This is just our cloud brightness, the first aerosol indirect effect. And in the regions just downwind of the Amazon, where we can sort of get to maybe where the Amazon influence sort of meshes with the marine stratocumulus region for those susceptible clouds, we end up getting quite a bit of cooling in these regions on the order of 0.4, 0.5 watts per square meter. But when we average this over the entire globe, the climate effect is 0.03 watts per square meter. So with all that hype about these molecules, going to save the world and stop global warming, according to our calculations at least, which we thought we were being sort of favorable in terms of reaction rates and whatnot, this is essentially a blip in terms of the uncertainties in our radiative forcings in our models from other reasons. And so, in our opinion, the Criegee matters a bit for sulfuric acid, but in terms of climate, it doesn't really matter all that much. So just to summarize this part, it can be important. The Criegee intermediate can be an important oxidant of SO2 near alkene sources. It can increase the sulfuric acid vapor formation by about 5% globally, or over 400% in the middle of the Amazon. But the CCN and indirect forcing changes are really weak due to microphysical dampening, and the fact that the changes are only happening in small regions of the globe, and most of the globe doesn't have any influence from this. Just throwing that up there again. And just as my group, I just want to acknowledge the person who helped out or was doing the whole first part of the talk is Steve DeAndrea, and he also helped me out for the second part of the talk too. So this group now, we're sort of fragmented. We're sort of mostly still in Canada, but some of the members of the group have moved with me now, and gradually people will hopefully be moving to Colorado with me. But yeah, thanks for having me, and it's just a great place to be in Colorado. There's more atmospheric scientists and aerosol scientists here per capita than I think anywhere else in the world, so it's pretty great. only if they're the first 2 or 3 generations, or the first and second generation of chemistry didn't break the alkene. So it's on the alkene ozonolysis step, which is where the Criegee can form. Yeah.
You showed that comparison with the HLS and compared to your model. I was wondering, could you grow the particles to CCN element sizes by having a lower rate of pressure, or are you really limited by the condensation?
Just put this up here for this. Yeah. There's probably 100 ways we can get it to match. So here, and actually all these simulations, we're assuming that our SOA is low volatility and just going to the surface area for these ones. So that going lower won't change anything there. What sort of happens here, if I look at this long enough, in these dashed lines, we have 100 teragrams of SOA per year, and these ones we only have the 20. This is actually 120, and this is 20. And it actually looks like we sort of overshot in this one. But that's also, I didn't mention, I had it up there, but I didn't explicitly mention, these simulations are 4x5. So our grid boxes in Huchila are like 400 kilometers by 400 kilometers. So Huchila is a remote location, but in that same grid box, we have cities in places that are emitting CO, and then we're mixing it, instantly across the grid box. And so there's potentially more anthropogenic influence in our model at Huchila. It's this one big grid box that has both cities and not cities than actually is in the atmosphere. So that's the trickiest thing for these comparisons, is we can't get things that are too urban or too remote. And you sort of need to get something that's representative of the grid box. So I'm digressing from your original question, but it's more just my disclaimer of how hard it is to get it to match, and then whether you should be matching a 4x5 grid box with a specific location. Yeah. Jose? Yeah, that was one of the things which stood out to us too, is that there were all of a sudden nucleation events there that didn't seem realistic. Yeah, because all of a sudden our sulfuric acid concentrations were almost a factor of 10 higher in this location. So. No, we don't explicitly account for the amines in the sense that we track them. It could be that the amines are one of the reasons why, if there's, say, acid-base chemistry going on in the smallest particles, it could be one of the reasons why that surface, assuming that it's low volatility and SOA just sticks to the surface area, gives us a better representation of nucleation events than if we don't. So no, we don't actually do it, but this fudge could be essentially accounting for that, maybe. I don't know anyone who's put amines into a 3D model. I know that Leah Hildebrandt, who was here, was working on the initial steps with Kelly Barsanti and Jim on trying to figure out the best way to do that. But I think it was still at box model stage when they were using it.
Your conclusion of this CCN condensate for very low volatility, but they got there by using less volatile. So, they were emitted in the gas phase.
Right.
Yeah. So how do you see that in more?
How does it get so low, you mean?
Yeah.
That's a completely open question. The possibilities are there's essentially 4 that I've been able to think of. One, the traditional gas phase successive oxidation sense, if it can happen quick enough, you get down to 10 to the minus 2, 10 to the minus 3 micrograms per cubic meter C stars, and then it condenses and it's stuck. That's just sort of, I'll call it the Neil Donahue means, because he's one of the people. We wrote a paper on whether or not gas phase oxidation could get you down that low. 2, you have something that's not actually low volatility when it gets there, but it goes through either acid-base chemistry or oligomerization when it's in the aerosol phase. And so when I say that it's 10 to the minus 3 or it's low volatility, it actually doesn't matter if it's low volatility or not when it first hits, but what matters is that if it sticks and doesn't re-evaporate, and as soon as it's in the aerosol phase, it's low volatility, because that's essentially the same thing. So if it goes through acid-base or oligomerization to become low volatility, that's a possibility. And then the third one is the phase. If somehow it is technically still a molecule that if you were in pure form has a volatility that's higher volatility, but somehow it's trapped because it's a semi-solid aerosol, that's a possibility too. Although I would tend to think that it would become semi-solid because there is something like oligomerization going on. And so maybe it's both that it's becoming lower volatility and it's semi-solid. It's just trapping it that way. But maybe this is something we'll figure out this summer, or slightly more. This summer meaning in our field campaigns, not just per chance figure out this summer. Yeah. Jose? No, actually, we should do that. Yeah, I haven't yet, but I mean, so Dom's grad student Kat actually has a means of just taking our output and doing that. So that we really should do that.